Next is a talk I've really been looking forward to. Our speaker is Bob Ciotti. He's the Chief Systems Architect, Supercomputing Systems Lead at NASA Advanced Supercomputing Division. His group has development and operational responsibility for all supercomputing-related assets at the NAS, including supercomputers, internal system networks, storage, archive, visualization subsystems, and other data analysis platforms. He currently manages development and operations for Pleiades, NASA's current primary supercomputing platform, a system that's the largest in the world of its type, an x86 Infiniband cluster without attached FP accelerators. Something you may not know about Bob is that he was on a rowing team that holds the record for crossing the San Francisco Bay. Rock on, Bob. Bob Ciotti, ladies and gentlemen.
Thank you.
Thanks for joining us on the show.
All right. Okay, so which buttons go forward and back here?
You have the black one, the wrong remote.
Oh. All right. We're just going to give a brief review, I guess, of the facility, what we do, some of the Lustre issues that we have, maybe some observations, some tools that we run. That's sort of listed here. So what is the system and what do we run? So the overall facility, which is, we've sort of referred to it as a ground-based instrument, is a collection of various types of computing equipment that are all used to solve supercomputing problems in support of NASA missions. And so they're quite varied. So they vary from space science to replacing the shuttle. There's some launch systems that we're working on. Ocean modeling. There's a shuttle ascent in here. There's all things that NASA does that are of scale, pretty much would be running on Pleiades at some point in time, most likely. So this is the result of a project called Kepler. So Kepler had a 95 million pixel CCD that it was using to take pictures of stars. And so it found this KOI, which is a Kepler object of interest. So that's a real star. The planets are sort of, cartoons, but it's a multiple system. So, there was a joke made about taking a file and per pixel. And so actually these stars on that 95 million pixel CCD array show up sub-pixel. And so through math, they can sort of differentiate sub-pixel. And so each one of those sub-pixel stars ends up with a bunch of files. And so, yeah, exactly. And so what's in the files are luminosity of the stars, and then there's a lot of mathematics that are run on it to find these transits, right? So you're looking for planets. And so this was interesting. It's one of this body of evidence here to demonstrate that there's probably more planets than stars, right? So that's a pretty cool thing, I think. Because of the number of files in this, we don't run it on Lustre, we run it on NFS. So we've got tens of thousands, if not hundreds of thousands of files that run through these when we get a slug of data back from the satellite to do these analysis runs. And so lots of little files are important, and there can be reasons, because these files, this information is stored in a great big giant database. You query the database, you shuttle that off to the computer, and you do a bunch of work and you bring it back, and you have to track all of the different instances of the data to be sure that it's correct when it gets to the different ends. And so users decided needed to be in a file. So we can't really say they don't know what they're doing. They obviously have constraints beyond the sorts of facilities and features that we can provide. Echo is an example of something that actually works quite well on Lustre. And so this was this is a smaller version, but of a very large-scale model, an ocean model, global, where we generated over a petabyte from, I think it was around 2 weeks worth of run on this. So what this model did is every hour of simulation time, which, or model time, so when you're looking in the real world, so down in the corner here you see the date kind of clicking on in 2003. There's observational data that goes into this, which forces the model, and then you forward step the model to make your approximation, then you correct it with observational data and move it on to try to understand what the ocean actually looks like. And so in order to even refine this further, the scientists were on this project, we're dumping model data every hour of model data time, which translated to about every 2 minutes of simulation time. So every 2 minutes we needed to dump about a half a terabyte, and we wanted that to complete before the next time step went, so you're not holding up the calculation. And in order to do this, you had to write some additional processes that collected the data and then streamed it off to disk, because the model orientation, the matrix associated with all these data, is different than the way that you store it, because the stored order is based on sort of what makes sense globally on the Earth, and the model formats are what makes sense for how much memory you have per node, how many nodes you're running it on. So you have to do this translation. And so there's quite a bit of work in remapping it and then streaming it out to disk. So this actually worked pretty well. Streaming rates up to about 10 to 15 gigabytes per second on a dedicated file system. So Lustre can, in the right circumstances, really work well for streaming these large data sets. And actually here's a frame of the movie that was made, and I think this was a lot of impact associated with this analysis. And so the oceanographers, when they looked at this, they said, does the ocean actually look like this? It was like, wow. I mean, the amount of detail with the flow here and the dynamics involved, and so it's really incredibly valuable and exciting. Actually, it's really cool. Planetary Defense. So the talk, the name of the talk was, we're going to save the planet with Lustre. Your life could depend on it. So when I talk about this planetary defense, people say, what are you going to defend us from the aliens are coming? And I always say, well, no, that's just the Air Force, and they won't tell they won't tell you about it because they know the aliens are already here, and if they did, then they would know what we're doing, right? So, but no, planetary defense is, you've got all of these asteroids floating around, and occasionally they come in and they land, turn into meteorites, and they can have dramatic impacts on the planet. So if you located one of these, or could you locate these, and what would you do about it? Could you destroy it or move it? And so this is just a Russian mock-up that I pulled off the web. And so down in the corner over here you see, there's data processing here. So this is, sort of identifying the threats, doing some computation, and then maybe directing some launch and intercept mission or something. It's pretty sci-fi down the road, but there's a computer right here, and it might be a supercomputer. And so if you were building a system like this, would you put Lustre on that supercomputer? If the penalty for an L bug was you missed, right? And so just think about that a little bit. So so my Lustre support people at Intel, so when you're asleep at night and you wake up because you can't sleep, You go over and check your computer to see if there's any L bugs coming in from NASA, right? And then if there aren't, then you can go back and sleep soundly, right? Anyway, a little facetious. But this is actually the bottom of SLS, which is the Space Launch System. It's a big project in NASA. We're replacing the shuttle. There's going to be people on this vehicle, and so there's all sorts of analysis with all the different elements of this vehicle. So people's lives do depend on it, and they're running on our machine and running on Lustre right now. And so with these systems, we do need reliability, and we do need to prevent file corruption. There's very important missions associated with this, and all the labs sort of have these different missions that they perform. But we'd just like to make the impact here that people's lives and the things that we do are critically dependent on the systems that we're building. Excuse me. So the computational landscape at NASA, this has sort of had this chart for a while. It's varied, right? And so we don't run one thing, we run hundreds of different things, if not thousands of different things. And they vary from, sort of the things that are on the chart here. And so I won't read it, but it's all over the map. And we don't have a lot of control over these different elements. These are very complicated, sophisticated, big software systems. And I think it's been said that, well, gee, all you have to do is modernize your code. And so for many of these projects, these are the most modern and most sophisticated codes that there are. They get the right answer. They compare to simulation data or test experimental data. And so they are it. That is, they don't get any more modern than that. And so that's kind of what we have. And so when you're going to go build the shuttle replacement, we're using those models because they give the right answer. So these are sort of web polls from, if you go to the NAS home web page, this is showing just sort of usage between the various missions. And because everybody's interested in what piece of Pleiades are they getting? Or is it fairly being divided up? So we're accounting for all of the cycles that we give. And here's a snap from last weekend of sort of what's typical on the system. So there's 1,000 jobs queued, 668 running on the system right now, or last Friday. And the most nodes used per job was 582, and the most CPUs, 10,000 or 11,000. Longest queued job, 8 days, so those vary from 8 days to 15, and to very short runs. But the point of this slide is that we really have this varied mix of jobs that run on the system. And it's fully booked, right? So I think probably all the labs could say similar things, that the number of available nodes here is, there's 19 free Westmere nodes and 35 Sandy Bridge and 15 Ivy Bridge and 69 Haswells. So that's out of 11,280 or so. And so it's fully booked and people waiting in line. This is file system utilization, and so we typically run our file systems at about 80 to 90% full, and we don't delete any data because we view that as sort of counterproductive. Users get really good at, some users, at running little scripts to touch their files, or they'll even disguise them as like things that you wouldn't identify as a touch, but they've figured out how to sort of go under the radar. So we basically contact users and try to get them to manage their file space when they hit their limits. here's sort of a snapshot distribution of file sizes, and so what it's showing is that 60% of the jobs are 1,000, or 60% of the usage of the system is 1,000 core job or larger. And so if we went back in our historical records, you'd probably see that. I think, say, half the cycles goes to jobs that are 2,000 processors and bigger. So that's smaller than, you know, maybe the hero numbers that you might see on some codes, and some codes actually do run quite a bit better at counts larger than that. But the scientists will size their codes to minimize the scale loss, right? So they're typically running thousands of simulations, and so there's a balance between this feedback of getting work done and what you throw away on parallel efficiency. And so you don't want to spend your money running an inefficient large-scale job when you can run 2 of those in the same time for 20% less money. And so they kind of find that right balance, and that right balance seems today about 2,000 cores. So this is the topology of the system. So Pleiades in general is an SGI system. It's a multi-dimensional hypercube, partial 11D hypercube, and it's dual plane. So each of these big graphs over here represent one IB network. So there's 2 IB networks, and every node connects to a vertex in that multi-dimensional hypercube. And then we implemented some changes to the subnetting to allow us to hook switching up to that hypercube within the same L2 network. So that's what we use to connect all of our I/O infrastructure up. And we've updated this recently. I didn't have a chance to change sort of the cartoon about the number of switches, but we actually have 16 switches in our outboard I/O infrastructure upstairs and downstairs, which is you know, what's referred to as 999 and 998. I updated the gigabyte per second nodes or numbers, and so that kind of tells you what the connectivity is between the various elements. And so the hyperwall down here is a viz system, and so that's one of the things that was used to generate that visualization data for Echo. And then about 105 OSSs, and so those include production OSSs and test. So Pleiades in 2008 started out at 64 racks, and then we incremented up to 92, and that was in 2008. And so that was number 3 on the top 500. So it's like, well, why are you talking today? So it's an old machine. Well, so what we've done is we've taken an approach where we're incrementally updating the system periodically to add capability. So over the years, what we've done is increase the number of racks by adding more and more. And so by 2011, we actually still were able to maintain it at a number 11 position on the top 500, but this spec, which is spec base FP rate, which sort of tells me what NASA codes would do, is probably about 5th in the world back in 2011. So that ignores things like the cell processor, Blue Gene, or the SSXX vector systems. And so a spec is a number of 2-core UltraSpark 2s, so these are mega spec numbers, 1.5 million spec. And so, but rolling in equipment and rolling out equipment can sometimes be disruptive, and so we're trying to actually operate the system while we're doing these updates. So users are using the system, we're cabling out the old racks and bringing in the new, and sometimes what that means is you actually have to raise the cables and take out the racks in the middle. And so here's a picture of what we had to do one time. So there's, I think, 12,000 Infiniband cables in our system. And so we had to lift up all the ones in the middle one time and get the new racks in. And so that was exciting. But this is all when the system's being used. So those workload numbers, fully booked, 1,000 people waiting in line, or 1,000 jobs, is sort of what we tried to do while we're growing the system. And so that continued back through 13, 14, 3.5 petaflops, 4.5 petaflops, and then today, Pleiades is 5.4 petaflops, and it's 168 racks. And so if I looked on, and this is an interesting chart here, of, you know, where does NASA fit, right? So if we were taking NASA codes and running them on any of the top systems that are out there, where would it show? And so this ignores GPU and Filesystems because we haven't really been able to adopt those yet. And so if I calculated, and this is a little bit different, this is done on memory bandwidth, if I believe the OEMs about what they claim their memory bandwidth is going to the memory system, and then multiplied that out by the number of sockets that they have, then we sort of see what the memory bandwidth in petabytes per second is. So K-computer, number one. It's not a surprise, I guess, to me. And so, but that's making some assumptions with the spec number about how that machine would perform, because I don't have spec data for that. Some of these I do. And the Blue Water machine, for instance, that didn't post a top 500 number, but you can calculate out the memory bandwidth number, and so that comes in at about number 3. And so what this says is that, you know, from 2008 to 2015, Pleiades is still able to sort of be in that top 10 type systems in terms of the amount of performance and what we're delivering back to the NASA user community, doing this sort of periodic upgrade approach. So what is it? Said 11,280 nodes. There's a Viz system, 128 nodes, GPU nodes, Xeon Phi nodes. So when we have systems that we want to test, we bring those in, connect them up directly, and so that means that they get Lustre access, they get access to all the other facilities that we have. We run our standard releases on them as much as possible, and then there's archive systems and data analysis nodes and sort of all of the other things that the scientists need to solve their whole problem, not just the compute piece. And everything's cross-mounted, so NFS and Lustre and pretty much the modules environment, it's all consistent across the whole machine. So Lustre-wise, 996 OSTs, 86 OSSs, and those are the aggregate performance numbers. So we're getting about, these are measured, 141 gigabytes a second in write bandwidth and 120 in read. And we're right in the middle of doing another expansion, so I want to add on the order of 15 to 20 petabytes this year. And if I could add 100 gigabytes a second of I/O bandwidth in that structure, I'd like to do that. So this incremental approach sort of allows us to be strategic in timing our buys so that when we need storage, we can buy it, plug it in. When the processors are ripe and it's time to add those, we can add those in. And so it allows us to, I think, better match against the technological availability and applicability of these various pieces that we want. So here's a bunch of reasons why incremental expanding sort of maps best to our budget process. I don't say this is always going to be the way that we do it, but there's, I think, always going to be an element of incremental expansion in anything that we do. In our production software environment, we carry several different system images. Typically, most of these are test, or for one reason or another, small community may want them. But it's a little cloud-like, and we'd like to do a little bit better job, I think, in this space of being able to freeze images and to allow people to go back and run things. And so there's some new sort of exciting things in the Lustre space that might allow us to do that. So this is What's today's general purpose supercomputer? Well, I think it's really this supercomputing environment that's important. All these elements, how do you pull it together and sort of adapt and move with over time to the technology as it changes, and so that you're not caught doing the wrong thing too long, right? So you want to be able to sort of adopt the technology when it's right. So within this, we have this concept of continuous availability. So we never want to take the whole system down. Outages are disruptive to users, and the dedicated time is very costly. And so what we tried to come up with is a way to do all of our updates incrementally. So that's the client images, the Lustre file systems, all the different elements of that instrument, they all have to have software updates, and so we try to figure out how to do it without taking dedicated time. And so one of the reasons is that, so if I need to work on one file system, then I want to run all my compute nodes on the work that needs to get done in all the other file systems. So a user is assigned typically to a single file system, so I can schedule it as a resource. And so if a file system goes down, we can eliminate the resource and then schedule all the CPUs on the remaining file systems that are still working. So it allows me to keep all the compute busy. We talked about the rolling updates. And so the continuous availability also applies to how we grow the system. So there's some tricks that we have to do in order to add equipment in terms of the Infiniband network. But what the users typically see at the end of adding equipment is there's just more nodes in the queue. Right, so the jobs just kind of flow through, and they've got more nodes, and they can go. And so that's the nice way to think. Some always doesn't work that way, but it does work that way quite a bit of the time. So I think we've got some refinement to do, but we're not doing bad. This is one of the things that we do for Lustre statistics at the end of the job. So because there's so much going on, it's very difficult for us to track every single user and every single job. So what we decided to do was to put Lustre statistics in the epilogue of every job that runs. And so here you see this user who actually, he is a rocket scientist. He sends me email occasionally when, so he called or sent me an email that day, says, my job's supposed to be running at 86.4% efficiency, and I'm not seeing that, right? And so what's up, what's wrong? So I go and look and figure out, well, it turned out to be a memory placement issue on the lead node with Haswell, specifically having to do with when he was reading his restart file. So the restart file comes in, he reads it, timing's bad, and so sometimes you get bad placement of pages, so it ran slowly. So it took a while to figure that out. But this also tells you how many opens and closes that you do. So over here, over about 10 hours, he did 1 million open and closes on some collection of files. It's 816 CPUs. And so you think, okay, well, that's one code, that's not that bad. Well, he runs about 10 or 20 of these at the same time, and then there's the other 500 jobs that are doing the same thing. So it can go downhill pretty quickly in terms of the kind of performance that we see with various aspects of the system. But anyway, it's kind of a nice way to provide feedback to the user. So sometimes these numbers are really skewed. So we see here we're doing a lot of 1 meg IOs, which is by the time the IOs get to the back-end file systems, they appear randomized, right? So in our workload conditions, the back-ends basically see 1 meg random IO, and so that's what we benchmark against in terms of our storage procurements. And so we can get better numbers, but in typical day-to-day operation, we don't see that. Here's another thing with Shift-C. I know so there's been some work done in Robinhood. Shift-C is a local tool that we wrote. In these big complicated environments, it becomes not a straightforward process to move your data from Lustre to the archive system. And so Shift-C tries to do it the right way, and it's threaded, and it's multi-node, and so we can get multi-gigabyte transfers going with Shift-C, and it sort of optimizes the network path based on the source and destination of the files. Log file analysis tool is something that we wrote Lumber, which goes through all of our log files trying to find out what went wrong with the job. So you've got gigabytes of log data, and something went wrong, you've got to paw through all of that. Well, what this does is it actually does that for you. So you give it a job ID, and it'll go through every log on every system that was involved and print it out during the time frame that the job ran. And so I get an email every day that says what failed, and by percentage, right? So those are over here. So some of these are job experience out of memory condition. So that's really not something that we could control, but there can be some other things in here that indicate that something's unhealthy in the system. And so it tells us the percentage of the SBUs, how much of the workload, and then you have weekly totals. And so it sort of lists all the different types of errors that we might have seen and the failure rate. So this was 14,650 jobs this week, 148 that failed for these various reasons. And so a lot of them are happening at startup, but some of them aren't. And so the ones that aren't at startup have higher SBU charges against them. So this is Monitor for monitoring InfiniBand traffic. So this is a way within the Lustre context to monitor the ports that go to all your I/O elements to tell what the performance rates that you're getting. So I can monitor all the file systems simultaneously, so we get a picture of how much I/O the entire system's doing at once. And that's a little bit old, but we see it fluctuate up into the 20, 30 gigabyte a second number, and sort of a day-to-day operation. Metadata caching, we turn this feature, so this is something we've done locally, so we actually read the OSTs to find where the metadata is. That includes the bitmaps and the inode data. And so you read those in through the raw device onto the OSSs and then turn off read caching. And so what this does is when a user comes in, and one of my users was having a problem the other day, and I said, well, how's it going? So he changed to his directory. We had 150,000 files, did an ls-l with color, and piped that to some Python script, and it printed out a graph, when every file was created in the last, week, and said, oh, everything looks good, right? And so what he just did right then probably initiated 1 million or 10 million metadata operations. But that's what users do. I mean, so they have piles of files. They want to look at them. They want to see how big they are. They want to see when they were created. And they want it to be interactive. And so what Lustre really needs to do is work on this. How are we going to do millions of IOPS and metadata to provide users the information they need to do their work, instead of how do we get them not to do it. It's how do we get the capability in there to do that on these large file systems. So what do we want from a file system? Well, want it to be reliable, easy to use, have performance, and to be free. And so those are hard, right? That's square. So is it reliable? And so I think Lustre-wise, things are surprisingly reliable for what we're doing, how complicated these systems are. A single OSS going down doesn't kill everything, right? So it's typically constrained to a few clients, limited number of evictions. We do a thing we call suspend resume, which is something we do in maintenance, which is you send a SIG stop to every process on the system. So you suspend it, run L-flush on all the nodes, and then maybe we'll reboot all the OSSs, or we'll reconfigure the InfiniBand network. We might do that for 8 or 10 hours. But then when we're done, we can resume everything, and we didn't have to take a dedicated time to do that. And it's because scheduling the dedicated time is problematic. If we have a window where the machine's just not there and it starts up where it left off and kept going, that's great. And so we'd like to actually see some more sophistication in Lustre where this is. Some things, reliability, are problems. We do see cascading failure sometimes where you hit an L bug and then everything drops into KDB. And so when we see thousands of evictions. And typically we always hit bugs that have patches, and so we've got some work to do in our build process and how we interact with Intel, who does our support. Is it easy to use? Generally, I mean, very. So people see it as a POSIX file system. So that's actually amazing that it can span from being something that people work on their desktop, run it on the supercomputer, and it works. So that's actually a real big success there. There's some odd cases around partial reads and writes, and so things that we haven't resolved, but for the most part it is very easy performance. You can get very good performance, and so you may have to really modify the application to do that. People aren't always willing. So we really need to deal with this issue of how IOs get randomized on big systems on the back end, and how can we optimize for that. Not how we're going to change the 1,000 things that we do on the front end to match what we can build. So we need to change what we build. And free? Yeah, I think it's free in the Stallman sense, which is actually incredibly powerful. It's been demonstrated in Linux that this is a really good way to develop sophisticated capabilities. And so I think we still have, we require high levels of support and bug tracking, and it's a steep curve in learning, but big parallel file system is a complicated beast. And so there's a few things in here where we'd selected the wrong, well, we got on 2.4 early, and then we couldn't get off because you've got this great big system. How are you going to move to 2.5? So not everybody, you might have users that have problems moving to 2.5, or we identify issues, and so it can take us months. And so Intel had stopped giving updates to 2.4, and so we had this problem where we start hitting bugs that are already fixed. And so I think there's some process improvements there. Resilience, I think there's some work to be done there. Single client performance is certainly an issue, and quotas seldom work. I think this is the final slide. So what we'd like to see: increased stability, better workload performance when you're doing 500 things at once, QoS, sort of limiting the damage of creative users, and an administrative shutdown. So I'd really like that administrative shutdown feature, which is, something at the Lustre layer that lets me flush all the caches so I don't actually have to suspend all the user processes. And so I think that's something we've talked about. So that concludes my talk.